Hi, everyone. Thanks for coming. My name is Bastien. I'm a compiler engineer and also a member of the C++ Standards Committee. So today I'm going to talk about an interesting topic, atomics, and specifically, no Sane compiler would optimize atomics. Now, this is a very clickbait title with a clickbait abstract. False. So the premise that I have is that compilers do optimize atomics, and it's not a silly thing, right? And they don't just optimize atomics, they optimize around atomics. They use a bunch of architecture-specific knowledge to optimize things, and it's kind of fun to optimize things when it gives you a performance win. And furthermore, I think that hardware vendors should give us new atomic toys to optimize stuff better, so we can use multiple cores in an interesting way. And the standard should also get better when it exposes atomics, right? So I'm going to try to convince you today that that's actually a good thing, right? Now, a quick disclaimer here. This is my mental model of lock-free code, right? So my goal today is not to convince you to use atomics, right? My goal today is maybe to dissuade you from doing so, because it's actually kind of hard. And I recommend that you watch Fedor's talk that he gave maybe Monday or something like that, and the talk that Hans gave yesterday, because they dive into how do you actually decide whether to do it or not, and how it actually works, right? What the technical framework is around it. What I'm trying to do today is just show you assembly, right? And I think my talk will have the distinction of having the most different types of ISA assemblies in this whole conference by like 2 or 3x. So it'll be fun. All right, so I think you should instead probably just use like the Parallelizing TS or MUTEXs or something like that, right? And again, the standard should get better in what it exposes to you. Now, I'm going to steal freely from Fedor's talk yesterday and show you, when do you want to use lock-free atomics, right? He had a nice decision diagram. And the really hilarious thing is the node that says, does it work? Right? Now I asked him afterwards, and that was actually a mistake, right? So he made a snarky slide without realizing it, and it's hilarious, right? But it really describes really well when you should go lock-free, right? So what I'm going to do first is just do a quick review, and I'm going to go really fast through this review, just to kind of show you what's in C++, what our tools are, and what we do with it. So in general, C++ 11 added a few things to the language. It added first a memory model, it added threads, and it added classes to communicate between threads, right? So the thing to remember is before C++ 11, threads did not exist, right? Now, that's the standardize view that there was something that existed, and some of what was exposed had to kind of take that into account. Now, what's interesting when we usually do lock-free programming or just multi-core programming in general is that the mental model that we have is actually not super related to how hardware actually works, right? So the way we like to think about how the hardware should work, right, is in terms of sequential consistency, right? And that's a pretty naive model, right? The mental model is really easy to understand. It's a zipper, right? Like you have stores that happens and they just kind of zip together neatly, right? Now, sequential consistency is that thing. It's really easy to understand. That's not actually how hardware works. And if you tried to use it this way, it would be kind of slow, right? So C++ has sequential consistent accesses, and they happen to not be the best thing. At that point, you may as well not use atomics at all. And it's really overly restrictive in expressing what you want to do. And I'll try to give you a few examples later. And Fedor, in his talk, also had a few examples of, not sequentially consistent, but that's close to what you want. And the reason it's slow is because it really limits what the hardware can reorder and limits what the optimizer can do, right? And in a lot of architectures, it ends up adding fences. And fences, depending on the architecture, cost from 2 to 200 cycles, right? That's a ginormous cost for something where you're trying to be fast. And so the way C++ fixes that is by exposing a model called sequential consistent for data race-free programs, right? So what that means is if your program doesn't have a data race, then you get sequential consistency, just kind of magically, right? And I'll dive into that a bit. So what's a data race? Well, a data race is what happens when two accesses to the same memory location by different threads aren't ordered. Now, that's really technical, and at least one of them stores to the memory location, and at least one of them is not a synchronization action. Now that's taken verbatim from the standard itself, right? I won't explain what that means in details and why that is, because that would be a wall of text, right? But the key takeaway to get here is that data races are undefined behavior, If you don't have data races, then you effectively have sequential consistency for your data race-free program, right? So the standard defines this in the section called Intro to Multithreading. It's 1.10 if you go there. It's beautiful, right? I really recommend you watch it. And Hans had the same recommendation yesterday in his presentation. Now, atomic operations. An atomic operation is indivisible with respect to all other atomic access to that object. And we have a bunch of memory orders in C++. We have relaxed. Relaxed is actually kind of interesting. So I mentioned, sequential consistency. Relaxed kind of breaks that model a bit. So relaxed allows you to have racing accesses. So one relaxed access to the same location as another one can't be reordered, but relaxed accesses to different locations can be reordered with respect to each other. Now, at the same time, the property of relaxed is that it is still indivisible, right? So you can't see word tearing. You won't see half of a write or something like that, or your write won't just half succeed through relaxed. And that's usually the fundamental property that people think about when they say atomic. They usually think about indivisibility, but there's a bunch more stuff that it actually means. And relaxed does enforce cache coherency. The thing about relaxed, though, is that it doesn't guarantee visibility, right? So hardware usually is kind of well-behaved, where like you'll have a cache and it'll become visible pretty quickly. But you could actually have an implementation of C++ in hardware where the cache doesn't really make the story that you do visible until you tell it like, hey, okay, maybe you should make that visible. And we'll see implications of that a bit later. So Hans had an interesting quote about relaxed in his talk yesterday. He said that C++ 14 replaced the offensive wording about relaxed with hand waving. Now that's kind of an interesting quote coming from someone who like was heavily involved in creating the language. He also said something else. When you use relaxed, well, it's probably incorrect if you care about the result, right? So it's kind of interesting, but there are valid uses of relaxed, and basically his entire talk was about that yesterday. So the basic tools that we have in C++ for doing atomicity are the atomic objects, right? So there's basic overloads, right? So it's just the class T that takes just whatever. And then there's an integral overload, there's a pointer overload, and maybe in the future we'll have floating point overloads as well, right? And the idea in C++ is that whenever you access things atomically, you always do so through an atomic object, right? So atomicity in C++ is based on the memory location object being atomic. It is always atomic. It's not, in this part of the code, I'm using this atomically, and this other part of the code, I'm using the same memory location non-atomically. And that has pretty deep implications to the programming model that you end up using. And other systems have different programming models. For example, the Linux programming model is based on the accesses themselves, right? So one part of the code could be atomic, the other part could not be atomic. And that's a fundamentally different way of expressing things. Now, atomic T has a bunch of operations on it, and they're actually kind of simple, right? You can do load, store, exchange, compare, exchange. You can see if things are lock-free or whatever. Atomic integral has a few more things, add, subtract, and whatever. T star can add and subtract only, and then floating point maybe can do add and subtract. We'll see. Maybe it can do more. Maybe we'll have like atomic FMA. That'd be kind of interesting but weird. Maybe we'd have comp exchange or something like that. Otherwise, you'd have to copy to the integer side and do the comp exchange. So after that, you have fences, and Hans's model of fences is just don't use them, right? The usual recommendation is that there's not really a good way to use fences or a good reason to use fences. His one explanation for where it is valid is when you use seclocks. Now, there's big disagreement around there, but I'll give you the example later where that's valid. And then there's signal fence, which isn't really about parallelism, but it's more about preventing ordering when there's a signal that happens, right? So a signal that interrupts your current thread. And then there's a whole concept of lock freedom. If you remember, atomic T can take just any T, right? So any T could be ginormous. Now, there must be deep magic if you can take a struct that's like a page wide and just make that atomic, right? Just do the write in one go. And what C++ does is it says, well, if the hardware supports one single operation that'll make that write happen atomically, so indivisibly, and that's cool, right? Then the access is lock-free. But if there's no instruction that'll do that, and most architectures just don't have a way, barring transactional memory, of making a whole ginormous write be visible in one go, then what C++ does is behind the covers, it has a bunch of locks hidden, right? And so if you access atomic objects that are way too big to happen in one shot, the atomic object actually has a lock behind the covers. Now, that's kind of silly. I'm just not really going to talk about non-lock-free atomics. It's kind of a weird thing to even try to make it work, but that's what the language does. Now, lock freedom is only guaranteed for one type in C++, and that type is atomic flag, and it's really not that useful. It does a few things, but all the operations I showed earlier, not all of them are available on that type. And the way I see it, and I may be wrong, right, but the way I see lock freedom is you have a comp exchange on your architecture that'll do that size, right? So on x86, you'll have like up to comp exchange 16B. Now that still doesn't mean it's fast, right? Comp exchange 16B in some cases is kind of slow. And then yeah, so I'm really going to focus on lock-free things for this talk. And yeah, so I just kind of want to show you a quick example of what lock-free code looks like. Now, it's a horrible example. Don't write this. It's not good code, right? But the basic idea is that you have like a publish-subscribe thing in this case, right? So you have a writer that writes a bunch of data. Notice that none of the writes of data are atomic. The only thing that's atomic is the flag that we have afterwards, right? So the writer writes his stuff, says, all right, here's this thing, I'm done, release all the things, and the reader says, oh, hey, I'm just going to wait until that flag is set, and afterwards it can read all the data, right? So spam, bacon, and eggs only get read once the flag is set, and if you use that protocol, you're guaranteed to have the results you want. Now, the idea here is that you run this into two threads, and there's a synchronization between the two threads, between the store release and the load acquire, right? And so it means that the writes that happened before in the writer thread are seen by the reads that succeed the load acquire. Okay, that's fairly simple, right? And so that's all the tools we have within C++ to do atomicity, right? So we have our tools, but why is the language set up that way? Well, it happens that it makes it easy to prove certain properties about the language and about like what can happen, right? And so someone actually spent a bunch of time writing a PhD to create math to represent that memory model and proved a bunch of interesting properties about the memory model and found a bunch of failings in the memory model that got addressed before C++ 11, right? And it's actually kind of rare in designs like this that you can use maths to like prove that something works in a certain way. So I think that's actually kind of cool. Now, the other idea is that like C++ doesn't get to dictate how hardware works, right? It's an important language, but it just kind of does stuff, right? And it kind of has to follow what hardware is able to do, right? So the abstraction was designed with a goal in mind that like you can write your code and it'll work pretty much the same on all the architectures if you don't fall into undefined behavior, right? And then the idea is, well, if it doesn't work correctly, you should use tooling like the sanitizers or something like that to try to find the bugs, right? Now, what I'm going to do is I'm going to go through a few architectures and try to show you how they implement atomics, right? So on x86-64, it's actually kind of straightforward. Load is just move, basically, and then store can be a lock exchange or something like that, and then fences are usually nothing, right? Fences are effectively, the way I see it, just a compiler barrier in x86, unless it's a sequentially consistent fence. So the compiler doesn't move loads or store around, and what that means is that the hardware just kind of executes things in the order that they are in the program, because they don't move around in the actual assembly, and afterwards they get observed in that order. That's just kind of a magical property of x86-64. That's what makes writing kind of tight code like that in x86 kind of nice, because it kind of does what you expect. At the same time, it means that if you wrote code for x86 and inline assembly, translating it to another architecture is kind of a headache, right? So having a high-level language like C++ makes it easy to translate code to another architecture. Now, notice that I'm not talking about comp exchange or stuff like that, but comp exchange is just directly an instruction on x86. It's literally like one instruction that does compare and exchange. Now, on power, it's kind of different, right? Power is kind of a weaker architecture, and so you kind of have to say when you synchronize to the hardware, right? And you also have to, instead of using comp exchange, there's these load link and store conditional instructions, right? So it looks like this, and it's kind of complicated. And when you do a comp exchange, you end up having a loop around things, right? So it means that it'll do a load, it'll acquire a reservation station or something like that, and then it'll try to do the store. If that fails, the store, the loop goes around and tries again and again, right? Now, I'm not showing 64 bits because that's even more complicated. Now, on ARM v7, it's actually kind of similar to power, right? And MIPS is actually really similar to that as well. You look at that and it kind of looks the same. Now, ARM has kind of extra interesting things where it has a bunch of fences. There's like a bunch of different types of fences. So DMB at the bottom is the basic type of fence. That happens to be a system-wide fence that like tells the entire machine, including hardware that C++ doesn't know about, like, hey, something could have changed. There's actually a bunch of other fences that exist in ARM, like DMB-ish. Ish stands for inner shareability, not like try defense. There's a bunch of other fences that exist, and then they also have like instruction synchronization barriers if you're touching the instruction, the iCache and stuff like that. And so it's actually more complicated to program in these architectures. Now, ARM v8 tried to make things a bit simpler. ARM v8 was designed with the upcoming C++ memory model in mind. And so it actually is kind of interesting, right? Like it has these load acquire and store release instructions. And so it's kind of like the life imitating the standard, right? So the standard did a thing and ARM v8 kind of did the same thing. And so it means that it's kind of a straightforward mapping in a lot of cases for ARM v8. Now, Itanium is another architecture that's actually kind of interesting. And the mapping in Itanium is actually kind of straightforward as well. So that's kind of interesting. Now, the last set of assembly I want to show you is alpha. So who's familiar with alpha here? Yeah, a few people. So what do you expect for alpha as a mapping from C++ atomics to the ISA? Not straightforward. Yeah, not at all. Right? It has a reputation of being kind of complicated. So what I did instead of trying to do that lowering, right, is I took an email from of all people, Linus Torvalds, explaining how alpha works. Now, what's interesting is that email has no profanities and it's actually super informative, right? Oh, I just missed it. That jumped around. There we go. So I won't let you read that email because it's really long, but it's super informative, right? And he actually explains how it works in the Linux memory model. Now, alpha happens to be kind of hard to implement for C++, and the C++ design kind of abandoned targeting alpha efficiently, right? Because alpha just wasn't really going to be a thing, and so they were like, we don't really care, right? But it does mean that some hardware can't actually handle the C++ memory model very well, right? So I guess that's the one exception that proves the rule that C++ is wonderful. Now, if you remember, like in the 6 memory orderings that we have, there's this consume thing, right? So who's heard about consume? Right, so does consume work well? Yes, no? I just hear laughter, no? Okay, so consume's kind of the butt of all jokes in C++. I'm sorry, Paul, if you're in the room, but it was really well intended, and the idea that consume had when it was standardized was, look, there's this thing called the address dependency rule, and I'll illustrate it for ARM because that's the one I know better, but it's similar in other architectures. And the idea there is that you have a load, right? So you load from R0 into R1, and then you load from R1 into R2, right? So if you look here, R1 is a dependency, right? The address of the second load depends on the result of the first load. And that's consume. That's all it is, right? So the idea of consume is you look at that and you say, hey, the hardware can't reorder things, at least in some architectures, right? That's not true in alpha. But when there's a dependency, the ISA explicitly said there's a dependency, therefore, the loads will observe the stores in the order that they occurred, right? And that's kind of interesting. It means that you don't need a fence between them like you would in other circumstances. Now, that's not quite true. What it does is it orders those two loads with respect to each other. It doesn't order any other loads. So if you had a fence, that would order all the loads, but without the fence, it only orders the dependent ones, right? Now, the problem with that is that C++ doesn't actually work that way, right? At the very high level, you could write code that looks like this. The compiler will not generate code that looks like this, right? If your code is a bit more complex, it's going to try to optimize around things because it doesn't know that you're trying to express a dependency way down in the back end in assembly, right? Now, there's even more complex dependencies that you can use in certain architectures. For example, on ARM, this works, right? Still no fence, but what's interesting is you're doing a load to R1, and then you're creating a magical 0. You're ending R1 with 0, right? And this is a 0 value, and then you're doing a register-register load. The base is R3, and you're adding R1 to it. R1 happens to be 0 now, right? But that still maintains the dependency between two dependent loads, right, without having the barrier. Now, we're going to try to fix consume in the standard, But right now, it just kind of lowers to load acquires instead. So it has kind of a barrier instead in basically every compiler, right? Now, I'm going to show you something really horrible, where I was working on code recently, and I kind of wanted to have consume because it turned out that in the code that I was working on, we had a barrier that was really slow. And I was just trying to order reads between two flags that barely ever changed, right? So what I did is I actually implemented consume in the most horrible way I can think of. And I didn't even clean it up to convince you that it's horrible. So, and don't do this at home. It's really, really horrible, right? It's really objectionable. Now, what's interesting is I talk to people and they're like, oh yeah, it looks like it'll probably work, right? Right, Richard? Now, the problem is he also said, well, except like the aliasing validation that you have, but whatever, right? Now, it happens to work, and it's actually kind of fast. Like I benchmark the GC that I was touching, and some specific benchmark in that GC got faster, so that's kind of interesting. But don't do this at home. But we'll try to fix it in language at some point. And we actually added some wording to the language that says maybe don't use consume right now, but we didn't fully deprecate it yet. So, we'll see. Maybe it'll come back. Now, I'm going to jump into, some architecture-specific stuff, right? So, in general, you program at your high level in C++, and then when you compile, you can tell your compiler, like, hey, look, I have this specific architecture, right? So if you're targeting, say, x86 or ARM or something like that, you can tell it it's this version right there, or it's exactly this CPU. And what's interesting is that the compiler can be smart and say like, oh, hey, look, I have this instruction that does exactly what you want. So I'll give you an example. On ARM, on ARM 32 bits, when you do a load of a 64-bit value, right? So it's a 32-bit architecture. You can do loads of 64-bit values, but what it does is it loads it into two registers, right? So there's this instruction called LDRD, load two things. Now, if you want to do that atomically, right? So if you don't want the load to tear, you have to usually use LDRDEX or something like that, right? Because you tell it, do an exclusive load and don't tear. Now, if you happen to know that your architecture has a long pointer address extension, I don't know why it's tied to that, but that's what it is, then you don't need LDRDEX, you can just use regular LDRD, right? So if your compiler is smart, there's a bunch of interesting things you can do by targeting a specific architecture. And it even gets more interesting, right? Some architectures have like transactional memory or something like that. Some processors don't actually implement the ISA the way it's specified. They implement something that's much stricter because they want it to, right? So if you go to your hardware people and you say, hey, I put a barrier here, is that the best thing? And they say, nah, actually, like, we lied and we didn't follow the spec and we made this thing much more strict than other things. And it'll be faster if you do this other thing, right? So I've worked on an architecture before that was supposed to be a super weak memory model, but it happened to be it was actually sequentially consistent when it executed, just magically, right? And so it meant that if I wrote code for the architecture, I didn't basically need barriers anywhere. I didn't need any special instructions. I could just use regular instructions, right? As long as the compiler didn't reorder them, everything was fine in that specific architecture. And then there's interesting stuff. So when I used to work on Chrome at some point, I was looking at the way Chrome used atomics, and there happened to be a really old CPU bug in old AMD versions 147 or something like that. So the really old Opterons. And that's like 0.002% of all the Chrome users. And it had to have a workaround for a specific bug in the way atomics work. So in that case, what Chrome needed to do is it needed to add an extra fence in places where the architecture said you don't need a fence. Right? Now that's unfortunate because it makes all the other users of Chrome slower, right? But it's kind of like your compiler should know better in a lot of cases, right? And so basically, sometimes you have special instructions, and sometimes it's even more tricky, right? You want to write a spin loop, for example. What's the best way to write a spin loop for your architecture? It really depends on the architecture and the specific version of that architecture you're in. And then, as I was saying, sometimes you can write code that's nominally incorrect that happens to work in that specific architecture. It's guaranteed to work in that specific architecture, but not in another version, right? So different ARM versions or something like that. And then, working around CPU bugs, right? So what's the takeaway from this? Well, C++ exposes things in a portable manner, but the hardware changes over time, right? You'll have bugs in old versions, they'll be out later, or you'll have kind of emergent patterns in the way people write code that mean that you used to write code a certain way, hardware adapted to that way. Now that's fast, or something like that. Or you do things and it's super inefficient, so hardware 5 years later or something like that gets faster, right? So you can actually go to hardware vendors sometimes and say, hey, like I do this, it's slow, and I don't have a way to make it fast. And then they're like, oh, let me think about that, and 5 to 10 years later, you get an instruction for your thing. You've probably forgotten about it by then, but someone else gets to profit from your foresight. And then, I have no clue what that is, whatever. And C++ in general just kind of works on data structures, which is kind of neat compared to like the horrible assembly that I had earlier, right? So it's kind of nice to program in that model, and also means that you can target what I call virtual ISAs, right? So I used to work on this thing called WebAssembly, where we would execute C++ code on the web. Now, the web happens to work on a bunch of hardwares, right? I think the V8 compiler targets 9 platforms, so write 9 individual ISAs that are different. So it has ARM and x86 and a bunch of other stuff, and there's no way assembly is going to work in that platform. But what does work is very high-level things like the C++ memory model, right? So if you take code that's compiled for C++, then it kind of just works in a virtual ISA like this, which is kind of neat. Now, how do we actually optimize atomics, right? I gave you like a bunch of individual tricks, but at a very high level, how does that work? Well, the C++ standard has this thing called the as-if rule, right? And so the high-level rules of data race freedom gives you sequential consistency is basically what we kind of hinge on to do optimizations. And the basic idea is that you're allowed to make things more atomic if it won't violate forward progress, right? That's one kind of benchmark for whether the optimization is worthwhile or not. And at the same time, we're allowed to make things less atomic if it doesn't add non-benign races, which weren't already there, right? So I'm going to assume your code doesn't have races, and then I'm not going to add more races. Basically, that's the yardstick for the compiler. Now, at the same time, this is all beautiful in theory, right? But the compiler shouldn't just go in and optimize things because it can without actually giving you any benefits, right? The point of saying, I won't add any benign races if you don't already have any, isn't like, I'll catch you if you do, right? The point is, it should be actually useful to optimize things, right? And so I think that's another kind of common misunderstanding. Like the compiler doesn't just go in and try to optimize your code into being incorrect or performing the wrong thing, right? The compiler tries to optimize things because it's faster in useful ways, right? And again, like tooling is there to try to help you catch ways where you make mistakes, right? So thread sanitizer or something like that should allow you to catch races in your code. Now, put another way, programs should just continue working if they were correct before after we've optimized them, right? If it was correct before, it should continue to be correct afterwards. Now, another way that I see it is that really the compiler should only be able to optimize what the hardware can do in a certain way, right? So if the hardware could reorder your instructions despite whatever you do, then the compiler should be able to do that as well, right? And so if you have, say, a loop that has a bunch of non-atomic things, nothing atomic in that loop, then that loop should be optimizable. The loads and stores should be optimizable as long as it doesn't create extra races. And pretty early on, when the C++ memory model was being standardized, they actually found a bug in, I think, GCC, where GCC would kind of speculate that the loop would execute at least once, right? And so what it would do is it would perform one iteration of the loop, right? Because it was like, oh, I'm going to guess this will execute once. It happened that the loop could execute 0 times, and so what it would do afterwards, after the loop executed, it would check, did this execute at least once? If not, it would undo the first iteration, right? Now, that happened to make the code faster, but it also happened to make it incorrect, right? So that's not a good optimization, and so GCC had to fix that optimization, which is, it's a bit unfortunate, but it's better to have correct code than fast code. All right, now, let's go a bit into what the compiler can actually do, and I'll try to show you a bit more code here, right? Now, as I said, I see it as like, what can the hardware do? One thing that you'll remember is I said, well, ARM v8 was kind of designed with a similar memory model in mind as what C++ has. Isn't that a bit circular, right? Like, the hardware is following what C++ does, C++ follows what the hardware does, and I'm saying the compiler can do whatever the hardware can do, right? That's kind of circular. That's kind of neat also, I think. Now, maybe we can do more than what hardware can do, and I'll give you a few examples of that afterwards. Now, we saw a few examples, and I'll show you a very simple thing. Here I have a bit of code that just does an increment, adds 1 to a location, and I have another one that does 2 increments. Right? Now, the obvious optimization for this is to just plus 2 instead, right? That's kind of straightforward, right? Like, wouldn't you be mad if your compiler didn't do that, right? Whether it's atomic or not doesn't really matter. Like, this isn't adding arrays, right? Like, it adds atomicity, but it can't hinder forward progress, so it must be correct, right? In this case, like, one fewer instruction, and there's no way that a valid code could have observed that you added 1 and then added 1, right? So that's why adding 2 is fine, right? Only racy code could have observed +1, right? And so what the compiler says is, I'll just assume you don't have races. There is therefore no way you could observe +1, right? Therefore, I'll just do +2, right? Straightforward, right? Now, here's a similar example, right? I have one version that adds 1, and I have one version that adds just a value, right? Now I'm going to lower that to x86. It's going to look like this, right? One of them does an inc. There's an instruction for adding 1 to a thing, and the other one doesn't add. Now, this is interesting, right? Those of you that know x86 right now should be shaking your heads, right? First, we're not going to win the Turing Award for doing this because it's kind of a dumb optimization. But at the same time, okay, they have a lock prefix. Both instructions happen to be 3 bytes. That's cool. But it may not actually be a good idea to do an inc instead of doing an add, right? And naively, you look at x86 and you say, you have an instruction to add 1. That must be a good instruction to use. Well, not really, because it happens that okay, it uses 1 less register, but it also kind of partially writes the flags, right? So x86 has a bunch of flag registers, and just partially writes one of them. And so it happens that in a lot of cases, add could be faster than inc. Right? And so you kind of have to benchmark those things before implementing them. So, maybe the compiler knows better, maybe it doesn't, right? But you would hope that your compiler vendors kind of tune their thing to try out to see whether that makes sense or not. Now, one thing that happens pretty often is inlining, right? And even with really tight atomic code, inlining is really, really important, right? And so that exposes certain optimization opportunities sometimes, right? So here's an example of code that does a compare exchange and then sees whether the expected result is the same as the desired result, right? And imagine that happens through inlining, right? So you didn't write dumb code, it just happened to be dumb because you inlined it, right? And that happens really, really often in just general code. It's nothing specific to atomicity. Well, that code could be changed to a compare exchange strong that just returns the result, because it happens that instruction already does what you want, right? And on certain architectures, what's interesting is that, so for example, on x86, comp exchange returns both the value that it loaded, and it returns a flag of whether that was the thing you wanted or not, right? So if the compiler is really smart, it can have both of these at the same time. Now, it happens that some compilers don't really represent such things very well, so it's actually kind of hard to optimize, right? But that's another problem that compilers can get better at. Now, here's a tricky one. It'll work for any memory order but release and acquire release, right? So what I'm doing is something where the desired value is the expected value, and I do a comp exchange with just whatever memory order I wanted to put in there, right? Now, that happens to be the same as doing this thing. Well, is it actually the same? Because I have this little dagger here, right? Not quite. The compiler has to transform this in what it calls, quote unquote, a release sequence. Now, release sequences are this magical thing back in 1.10, and it also has, oops, sorry, went a bit too fast. And yeah, so anyways, it actually has to kind of do a bit more work to do this properly, right? So I don't think any compiler actually does this optimization, even though it could. Now, here's another example. I have a load and I have a store. What does that look like? Any other instruction you would use instead? No, there's this exchange thing that you can do instead, right? So you have a memory location, you do a load and you do a store. What you're doing is swapping two things. What I'm doing here is I'm adding atomicity, right? Remember, there's no way this could have the first one could have synchronized with anything, right? It did a load and a store. But by making this more atomic, I'm going from two instructions, right? One that was a pure load instruction and one that was a pure store instruction, to having an instruction that is both read and write at the same time. And in some architecture, it happens to be better to have a write after read than it is to have an exchange instruction that does both at the same time, right? So that doesn't necessarily pay off, right? Now, okay, if you want to write deep down assembly code, maybe you can do that. Maybe you know the fact that this isn't faster or not, right? But I'm going to say this takes a lot of work to prove. If every programmer who writes inline assembly has to figure this out, whether it's faster or not, and in which architecture and which version of an architecture, then we're kind of wasting our time collectively as an industry, right? Whereas the compiler could just get it correct once, or just get it wrong and then get a bug file and then get it correct afterwards, than like everyone having to do that work, right? Just to be clear, compilers get this wrong all the time, right? So you should just file a bug if it's wrong, right? You figure out that it's wrong, you just like file a bug and eventually it'll get fixed. Or you fix it yourself, that's also cool. Okay, so far I've had kind of just toy problems, but I'll try to go into a more interesting problem. So I had a coworker, maybe a year ago or something, sent an email to a mailing list and said, I have this interesting problem, right? And the reaction you should have when someone says this, and it's like, you know, people interested in concurrency and compilers and stuff like that, this is the reaction I have, right? Yes, tell me more. And what he said is, well, we have this code, and it does this thing, and it uses atomics, but not really. It's like using multiple cores, but the code doesn't use atomics at all, right? And so he explained his problem. My code does a read, then it does a modify, and then it does a write. It was based on this paper that got published a while ago called Hogwild. And the idea is that you have a bunch of threads and a huge data structure, right? It's a huge data structure of floating point values. And what they do is they just kind of do racy reads and writes, right? So they do a bunch of computations, and then in that very big data structure, they have very sparse updates. And statistically, it's really, really, really unlikely that multiple threads will try to update the same location at the same time in their specific application. And that paper actually went out and proved that that was really statistically unlikely, and that if it happened that you did a read, then a modify, and then a write, right? So not an atomic operation, but you did these things separately, then statistically, losing one update out of so many doesn't actually matter, right? That's interesting, right? Now we're not in sequentially consistency land anymore. Very different, right? But it's an interesting property of that specific code. Now the problem is the code that they had looked like this. Who sees the bug? No one? There are no atomics in this code at all, right? So they have multiple threads updating this data structure, totally not atomically. That happens to be a race. It happens to be okay for their code, but it's still undefined behavior, right? But what's interesting is that on x86, the code that gets generated is this, right? Like that's pretty sweet code, right? Now it's not a read, modify, write. It's a read semicolon, modify, semicolon, write. Those are two distinct instructions, right? But it happens to be really, really fast. So they're like, well, we'd like to, you know, be standards compliant, but the problem is when we do that, it's really slow, right? So the first thing they tried, what do you try when you do this? Well, you add volatile, of course, right? And they did that, and the code that got generated was the same. And they're like, sweet, we're good. And we were like, well, but can you not do volatile? Like you have this big array and it's all volatile things, and like volatile doesn't really do what you want. And we'll go into that a bit later. But then they were like, all right, well, if we instead do this, is that correct? Right? So we have this atomic float, or this big array of atomic floats, and then we do a load that's relaxed, and then we do the modification, and then we do the store. Right? Is that correct? Well, kind of. Right? So if you remember, when we were talking earlier, relax doesn't really guarantee that things will propagate. Right? It doesn't guarantee observability. Right? But it happens that on the platform they were on, say x86 or whatever, well, it happens to hold the property that, like, once you do the store, it's visible pretty much there and then, right? So it happens to be correct, I guess, right? And the idea was, well, we do this thing, and that should generate exactly the same code as we had before. And now we'll have fast code, and we'll be standard pedant compliant, right? That's awesome. It's a great property, right? They wanted that, right? And the problem is they did that, and then they got this code, right? And that's 3 times slower. Like, what the hell? Right? Like, we want it to be all standards and stuff, and that doesn't, like, what? Right? So that's when they decided to send an email to the mailing list. And then I had the face that I showed earlier, right? The Gene Wilder face earlier. And I said, oh, let me try to optimize this, right? So I went in and got my hands dirty into LVM, and I didn't really know that part of the code base. I just made it faster. Right? Wait, optimization for the win. Now, the part of the story that I don't usually tell, and I'll tell it to you guys just, you know, for shits and giggles, is that I did that, And I think, how long was it ago? Like 2 months later, there's actually a bug caused by my optimization because I forgot to do one thing, right? And then that guy fixed it. It was awesome. It took forever to debug. It was awesome, right, Chandler? Yeah, awesome. Right, so like, it was a bug, sorry, but like, the rest of the code optimized really well. It's like if you use some really complicated thing in a completely different context that the optimization didn't work out so well. Right? But what I want to get to is that you can actually write correct code that'll be fast if you look at the code, and if it's not fast, then you like kind of file a bug or like try to fix the compiler. That's possible, right? Now, let's look at a few other things. The compiler can do a bunch of other stuff, right? It's just usually when it sees atomic or it sees volatile or whatever, just compiler throws its hand in the air and it says, look, I'm not going to touch anything. But if it were a bit smarter, it can do a bunch of stuff. It can do inlining, constant propagation. It can do a bunch of interesting tricks, right? Where like if you do all ones and you do an AND, and that's kind of like a load, right? It can do a bunch of interesting stuff like this, right? Now, those are all kind of really straightforward compiler transformations, and some of them are actually implemented in compilers, not all. Right, so what's the takeaway here? Well, if simple things are hard, right? Like some of the stuff I showed you is kind of hard. Then like your assembly code is probably not correct anyways, or it's probably not that fast. And it probably won't remain correct or as fast as it could be, right? Because as you upgrade your architectures, it won't. Whereas as you upgrade your compiler and your architectures, things usually tend to get faster for that new architecture, right? And usually the pushback that we get as compiler writers and as like people who give talks is, oh, well, I don't trust my compiler. Well, I'm sorry to break it to you, but you're already trusting your compiler, right? Like, you kind of have to. It's compiling your code. Right? You don't trust it to generate fast code, but you trust it for everything else. It's kind of silly, right? So you're really kind of diluting yourself in that case. And really, like, that's the question we get. What if the compiler emits suboptimal code? What do you do? File a bug, right? Or complain on Hacker News. That's also good. Right? But not on the comments for this YouTube video. I just don't look at the comments. Now, at this point of the talk, I was going to talk about sequence locks. They're a really cool little atomic optimization. The problem is Hans talked about it in his talk yesterday. So I'll just refer you to the YouTube video because he did a much better job than I did, because like all these slides are kind of taken from his paper, right? So I'll just skip over that, right? It's a really cool data structure. If you don't know about it, you should check it out. It's a thing aimed at just read mostly data structure. It's things that like a bunch of threads just read all the time, but you update it only every so often, right? And the code looks kind of tricky and it has a bunch of different things. The really interesting thing here is that we kind of want a release store, and there is no release store in the language, right? And so Hans came up with this really cool thing called read, don't modify, write. It's a cool optimization the compiler can also do. And what it does is you do a fetch add with 0. So what does fetch add with 0 does? What it does is it just kind of adds 0 to a location, which does nothing, right? And that's a way to tell the compiler, well, hey, I want to have a load, but I want this load to be release, right? Now that's kind of an ugly hack, but it happens to generate kind of interesting code. Or if the compiler were smart, it would, right? So there's different types of code that get generated in different circumstances for that. Whether you use the fence manually or whether you use the read, don't modify, write. And the interesting takeaway here is that if the compiler does its job well, you get nice perf speedups, right? So I'll refer you to the paper. It's a really interesting thing, but like in different cases, you write different code, the compiler optimizes it differently, and then things get faster or slower. And what's really interesting in this case is that for seclocks, it's not just that things get faster depending on what the compiler does and what code you wrote. It's that it'll depend on the architecture you're on, and it'll depend on how many cores you have, right? So in this case, it's the read, don't modify, write instruction. It doesn't really scale with the number of threads that you have. So that's kind of another thing to keep in mind when you try to optimize stuff, and when the compiler emits code, is that the code that you generate also highly depends on how many people are going to try to access the location at the same time, right? Now, as I was saying, you can do a bunch of other compiler optimizations on atomics. You can, maybe do dead store elimination, right? If I do 2 stores back to back to the exact same location, right, and it's back to back, I don't do anything in the middle, then the compiler can go and say, look, you did 2 stores to the same location, you're kind of dumb, right? Like, I'm going to remove the first store and keep the second one, because you know what? Unless you had a race, nobody could have observed the first store. Or, yeah. So you can do a bunch of other stuff. You can do strength reduction and things like that. And you can also even optimize relaxed axes, right? So here's an example where you have to read kind of this tricky code. I store to X and Y, but interleaved, right? Now, relax doesn't guarantee ordering between relaxed stores. So what I'm allowed to do in this case is I'm allowed to coalesce them even though X and Y were separate, right? They were kind of interleaved like this, and I moved them together and then collapsed them. And compilers should do this. I think LLVM does. I'm not sure if GCC does yet. Now, that leads to a kind of interesting question. When I initially wrote the paper that created the stock, Hans Bohm kind of flipped out. He was like, whoa, compilers do what? Like, I can't just write a progress bar like this. That's what it means, right? So what I'm trying to do here, and sorry, I've had relaxed updates, but I'm trying to do a bunch of really heavy work, right? So I have this loop that does heavy computation, and then I just increment progress, right? Now, what's interesting here is that I don't have any other atomic operations in that heavy amount of work, right? All I'm doing is I'm doing heavy work, and then I'm telling the progress bar on another thread, hey, I did one more work, right? So the idea here is the compiler should be able to unroll the loop and do a bunch of optimizations to the code because none of that is atomic except the progress thing, right? Now the problem here is that the compiler, in a lot of cases, is allowed to do this optimization, right? So it'll create a local copy of the progress thing. It'll just increment the local copy 1,000,000 times or something like that, and then just do the final update. So your progress bar looks like most progress bars do. They go from 0 to 100 in one shot, right? Now, that's not really what you wanted, right? But that's what you said in this code. And so we added some wording to C++17 to discourage this kind of optimization. Now, it's super hand-wavy wording. It's in a note. It's totally non-normative. And it says compiler really shouldn't do that in like weird cases, right? But in most cases, like you're actually doing synchronization. You're not just like fire and forgetting writes. And so in most cases, that doesn't happen, right? It's just kind of an interesting corner case where like, you know, this is sane code, right? Reasonable people expect this to work. And it happens that the standard says that this doesn't necessarily work. Now, I don't know if compilers that optimize this specifically, but as we start like adding new optimizations, we'll have to be really careful to not break real world code, right? Now, how do you disable the reordering or fusing that we saw earlier? Well, there's a few ways to do it, right? Now, this is super objectionable, right? Don't do that. Like, just don't, right? I say don't do that, and I showed you code when I did consume that did exactly this, right? That's leadership. Now, you could do signal fences, but you're like, what is a signal fence anyways, right? And signal fence was kind of put in there to kind of help like prevent this from happening, because if a signal happened in the middle and whatever, but it's kind of weird, right? Like, has anyone ever used signal fence or seen it in code? Like, when you see it, you're like, what? What is that? Right? That's kind of weird. You could use volatile. No, that won't work either. That's just a dumb idea. It won't work. And then, you know, just don't use relaxed maybe, but then like you're making this heavy computation like a tiny bit slower or something like that. Or you could synchronize with your progress bar, right? Like increment and then the progress bar decrements and you look at the amount and whatever. It's kind of weird. There's a bunch of stuff you can do, but it's weird. So let's look at a bit more of what you can do. Those are all kind of like regular low-level optimizations, but you can do higher level stuff as well. Right? So the compiler could go in, and that's all kind of blue sky thinking or whatever, but the compiler could go in and tag non-atomic functions and optimize around them, right? So the compilers already mark things as not doing any reads or not doing any writes or something like that. It marks aliasing and other stuff like that. It could mark functions as whether they have atomics or not and optimize around that. That'd be kind of interesting, right? Because usually functions kind of act as a barrier to optimization unless you're doing interprocedural stuff. That's kind of a basic kind of low-lying fruit that we could do. That's kind of interesting. It could do something more interesting where it proves kind of regions that don't interfere between each other and kind of optimizes around that. And that's not just about atomics, it's also about the non-atomics that are under them, right? So you could optimize things by proving that things don't just kind of touch each other. Then you could also optimize fence positioning, especially in languages that have like write barriers or something, like if you have a GC running concurrently and something like that, you end up having a lot of fences everywhere. And the fences aren't always positioned optimally. You have a big control flow and you have fences everywhere. You could kind of prove that the slow path has, you'll put fences in the slow path and remove fences from the hotter path without removing correctness, right? So it's basically like just balancing the fences in the control flow graph. You could do that. And then you could prove things like, oh, this doesn't escape. It's on the stack. So there's no way you could be sharing it with everyone else. Or this is in TLS or something like that, right? So there's a bunch of interesting stuff that we can do here. Now, at this point, you're all like, okay, well, atomics are really complex, and like, I'm not sure I want to use them anymore. I'm just going to stick to STD-MUTEX for sanity, right? Is that a good idea? Well, I think it is a good idea, right? It's easier to use correctly, in theory, right? But the thing is, you could still optimize STD-MUTEX, right? The compiler could do this, because basically, the way I see MUTEX, and I may be slightly wrong, but the way I see it is when you lock, you create an acquire, and when you release, when you unlock, you create a release, right? That's kind of what MUTEXs do. Now, the problem is, from the compiler's point of view, it doesn't actually know about STD-MUTEX, right? Like in the standard library, there's STD-MUTEX, but then the compiler parses that just like anything else, and then just generates code. It doesn't really know that it's STD-MUTEX. It kind of lies to itself. It doesn't look at the name and say, this is STD-MUTEX right there, look. Right? And the thing is, a good STD-MUTEX doesn't just have like a spin loop. That's a stupid STD-MUTEX, right? A good STD-MUTEX has things like calls to pthread or kernel calls or something like that to make the mutex faster in the case where you can't get the lock in a reasonable amount of time, right? And anytime you touch the kernel, compiler just throws its hand in the air and says the kernel can do whatever, so I'm going to assume you did whatever, right? So reasonably, I can think, well, STD-MUTEX doesn't optimize anything, but we're trying to add this thing called synchronic to the language, and that may change this thing, and we could actually start optimizing around STD-MUTEX. And that's kind of interesting because there's a bunch of interesting optimizations we can do. Kind of a parallel to that, if you have a shared pointer, for example, and the shared pointer, you pass it around, so it does a bunch of increments and a bunch of decrements, it'd be kind of interesting if the compiler could optimize these, because if you think about it, shared pointer, the only thing that actually matters is going from 1 to more than 1 and then back to 1, right? Everything above 1 just doesn't matter for a shared pointer, right? It's just a ref count. It's like, it doesn't matter, right? And and the compiler can look and say, look, I did 1 increment, so it's above 1, and after that I can coalesce all the increments and all the decrements. Now, it's kind of difficult to do that in an interesting way for the compiler because it has to look at the decrement side and say, oh, I am decrementing, and there's always a branch that says like, hey, are you going under 1 or something like that, right? So that's kind of hard to optimize. But at a high level, that's kind of interesting optimization, right? Now, we know how to do better than STD-MUTEX, right? The STD-MUTEX just knows better than you do usually. Now, I'm going to skip over this really rapidly because it's objectionable, but we could talk about volatile a bit, right? And the basic idea of volatile was like memory mapped IO and whatever. And it's kind of silly. It doesn't really map to what C++ does anymore, right? It doesn't really mean anything that's very coherent, right? Does it prevent low store motion? Does it do arithmetic or whatever? It's really weird to do a volatile. And does it allow you to do shared memory? I don't know, because it gets better. All compilers model volatile differently, or a lot of them do, right? This version of GCC does one thing, MSVC does another thing. And what it does is just really crazy, right? Like it gives you a bunch of guarantees unless you break a rule, and in that case, it just doesn't do anything. Right? So Clang actually emulates that weirdo behavior that MSVC has, right? And that's like an olden mistake that they made, and they try to fix it when they did the ARM version of MSVC, but like they can't really fix it because people currently rely on the behavior of volatile, right? What does it really mean? I don't know. Like I have no clue what volatile means, right? It has a few things that it says that it does, but like it really depends on the implementation. And then there's a bunch of weirdo questions like, can it be lock-free? I don't know. Can it do read, modify, write? No, not really. And then are there portable uses of volatile? Well, I would say that maybe there are, right? Maybe these 3 uses are valid. Some other people would object, but whatever, right? And then there's also volatile atomic. That's kind of weird, right? And what do compilers really do? It's weird. It's weird. So what do compilers really do? Well, the standard library looks like this. It has C atomic or stood atomic, and then it kind of lowers to instructions that do built-ins, right? So the compiler looks at this, and it's like, oh, okay, well, I'm going to like kind of just generate those built-ins, and then I'll optimize a few things in the front end, but it's really with the middle end where things happen, right? So it has these instructions in the middle end. LVM knows about loads and stores, and it tags those loads and stores as atomic, right? And so as soon as it sees atomic in a lot of cases, it just gives up. It's like, nope, not going to touch it. Right? And then it has other operations for read, modify, write, and comp exchange or stuff like that, and it has fences. And then in the IR, it says like, oh, is this simple? Is it volatile? Is it atomic? And then just don't really touch it, right? So what we've been doing is adding things where it actually touches stuff in very tricky ways. Like we actually think a lot about the patches before touching things. And then in the machine IR, if you remember the example I gave you earlier about Hogwild, that's where I modified what the x86 operations do, right? So it's really similar. So in general, conclusion, I'm almost done. What's the takeaway from my talk? Well, I kind of want the standards committee to assume optimizations occur and actually encourage them, right? Like not everyone on the committee assumes that that's the case for atomics. And I want us to standardize existing practice, right? Like as I was saying, not everything that we have actually makes sense for everyone, right? But the goal is that C++ allows you to express things as close to the metal as possible, right? And I would like the language to do that better. And then this is madness to use in a lot of cases, right? So I'd really like the libraries to get better at making it trivial to use these things, right? Like kind of higher level stuff that allow me to express concurrency and parallelism really well, right? And the goal is to make it hard to get that wrong, right? Atomics are easy to use the wrong way, especially relaxed. But if the library exposes something, then that should make it easier to use it correctly, right? Now, most of you in the room are developers. What should you get out of this talk? Well, you should really drop inline assembly, except when like the language fails you, right? If the language fails you, sure, go for inline assembly, it's cool. But at the end of the day, like it'd be great if everyone used atomics and the higher level stuff the language has. And then, if it's wrong, just file a bug, right? And talk to the standards committee. Like in a lot of cases, we'll do things without having any clue of how people actually use it, right? We'll have one use case for a thing and we may just get it wrong. So it'd be great if people gave us more feedback. And then there's all this tooling that you should use, right? Like thread sanitizer and stuff like that. That would be great. Now, I don't know if there are any hardware vendors in the room. I saw a few like Intel people earlier, but like it'd be cool if like we could use more stuff, right? Like showcase what you have and like make it useful. And in the standards committee, we've actually been trying to do that, right? So one of the things we're trying to add for the next version is SIMD support, right? And we're having kind of hot debates on how to do SIMD properly in the language because it's actually not that easy. And then the last takeaway is for compiler writers, like just, get back to work. Because there's a lot of stuff that we can do. And obviously, like there's stuff that we can do, we should focus on the ones that are useful, right? There's all these optimizations that we can do. A lot of them just aren't that useful, right? So we should find interesting code and make it faster. All right, so that's it. I have a bunch of references on GitHub if you want to check out. Like I have a bajillion papers and other stuff if you want to read more about this, because I know I went kind of fast over a lot of stuff. But if you go to GitHub right now in the README, I have a bunch of references at the end. Some of them are C++ standards committee papers. Some of them are just kind of regular publications or like, the references to what different compilers do and stuff like that, right? So any questions? All right, 100% clear. Thank you.